Good morning, everyone. Hello and welcome to this session. I am Harini Ramakrishnan. I'm a program manager at Microsoft, driving network data plane initiatives and particularly DPDK for Windows support. Um, Now, this session today is a joint session from among the multiple partners that are working to bring Windows platform support to DPDK. I'm representing Team Microsoft, and we have partners from uh, Mellanox or NVIDIA and Intel joining us this morning. And behind the scenes, we have tons of other contributors that we are representing here today as well. So we can get started momentarily. So the agenda today is we're going to talk about briefly the motivation and the journey that we've had so far, and where we are with respect to Windows platform support. Um, and then we'll go through some demos and talk about our challenges, roadmap, and we will stop with Q&A. Now, let's take a moment to talk about the motivation. Now, Windows developers have expressed a need for a high throughput, a low latency data path for their workloads. Now, here in orange is a quote from a customer, which kind of sums up the sentiment that we have received over the past couple of years, which is to say that they've tried about all inbox solutions that come on Windows, including Rio sockets, Windows sockets, etc. And they spend a fair amount of time, going through the technology and familiarizing themselves and benchmarking it. And the net result seems to be that you kind of don't get a DPDK like performance, which seems desirable from the community. We have heard from our partners, developers in the ecosystem about the need to have a kernel and a network stack bypass solution like DPDK. Not just that, the Windows networking stack has improved its cycles per byte optimizations right from Windows Server 2016 to 2019, and then from 2019 to 2022. But we are kind of reaching a point of diminishing returns for all the investments that we are making. The performance improvements that we are seeing are not comparable to the network stack bypass technologies. And that is one of the reasons and the motivations why we want to make DPDK a viable solution on Windows platform. Um, Not just that, the Windows networking stack is at the cusp of multiple transformations at this time for future-proofing architecture, and at the crux of all of that is the DPDK support. So you will start to see many solutions come up, even first-party solutions that come on top of DPDK and using DPDK. So that's one of the reasons why we are wanting to make sure that DPDK support on Windows is prime time and mainstream. Now, moving on. So I want to quickly recap the journey that we've had so far. Back in 2017, we launched a DPDK fork for Windows support. It was a disconnected repository. It had a separate development and building pipeline. It trailed behind upstream community maintained repository and was pain to maintain. And we talked about it multiple times at the 2017, 2018, and the 2019 summit. Then in 2019, the upstreaming work for Windows platform support into the main DPDK repository began. And ever since then, the contributions have come up, and the upstream support has accelerated. Microsoft, us as a team, joined both as a contributor and as a sponsor back in 2020. And since then we have seen the community expand with not just Intel, who was our primary contributor early on. Now we had partners and our friends from NVIDIA. We have Cisco, Marvell, and multiple subject matter experts from the wealth of the DPDK community so far, and independent software vendors such as Maya Data, DataPath, and many more that have joined us in this effort to accelerate Windows platform support upstream. So much so that we also have a storage platform development kit for Windows that is based on DPDK, forking off and available today. I will leave some slides in here for any of you that will be interested to see the progress that has been done with SPDK in the future. Um, Moving on. Um, Now, I'll quickly take a moment to recap where we are as of 21.05 release that came out in May. Now, we have about 15 odd code libraries that are validated to run with Windows. And not just that, we have the kernel mode drivers, NetUIO and Vertifice that support Windows today. And we have hardware pool mode drivers and software pool mode drivers, including Mellanox 5, Mellanox 4 and above, I40E, ISPMD, and the software PMDs that we have, PCAP and VMXNet 3. We have multiple hardware, vendors that support DPDK for Windows today, and we have multiple sample applications that you can test out today, notably L2 Forward. A subset of test PMD also works today. In terms of the tool chain, we have Mason plus Ninja tool chain and a Clang Ming GW compiler as well. We also have compilation gates at the UNH lab, just with Clang and Ming GW. In terms of compilation, we expect to add unit tests and DTS tests soon. That's on the roadmap. So now I'll pass it on to Dmitry K for taking it forward from here. Dmitry?
Yeah. Please follow Harini. Yeah, hello, my name is Dmitry Kozlyuk. I've been a Windows community maintainer for DPDK from the past 2020. I'm going to talk about some challenges that we faced when porting the core DPDK libraries, mainly EL, to Windows. There were many of them, but I'll try to focus on those that most vividly show the nature of Windows specifics. The first one would be thread local storage variables defined in shared libraries, the DLLs on Windows. The problem with them is that portable executable format used on Windows doesn't have a special section for such variables. So basically, you cannot use them without some support from the compiler. And different toolchains solve this problem differently. Clang only works with such variables within single application, within single binary, and it doesn't work with DLLs at all. What's most embarrassing, it compiles such apps, but runs them with errors. And MinGW, which is basically a GCC port for Windows, uses simulation for thread local storage. It comes with some performance penalty, of course, and then there are some issues with exporting those variables, but at least it provides a working solution. You can find more if you follow the link to the demo code if you want to learn the subject. And I'm also glad to say that Microsoft is working on a solution that will work for all tool chains. Next slide, Harini. The second interesting point was alarm support. Alarms are treated as a kind of software interrupts in DPDK. The model is that we have an interrupt thread that waits for alarm to expire and executes a callback. And similarly, Windows does have all the facilities to implement that. It has a function to set waitable timer. It has functions to make an allotable wait for that. When the timer expires, it will call the callback, so we even don't need to execute it manually. But the catch is that these two functions, the setting timer and the waiting for it, must be executed from the single thread, that is, from the DPDK interrupt thread. So what we have to do, we have to pack the job to call the set waitable timer to a special kernel object, to pass it to the interrupt thread via the system call, and then the interrupt thread will set the alarm and wait for it in a usual loop. This way, we both satisfy DPDK model requirements and comply with what Windows offers us and wants from us when using this API. But the most challenging part of the API was unmistakably the memory manager. On the next slide. Memory management in EL consists of three broad layers. The first one is RT malloc API. then comes the malloc heap allocator, and then the so-called memalloc part with which users don't interact. It allocates huge pages from operating system. It can operate in legacy static mode when it uses static memory layout, or dynamic mode when it allocates huge pages on the fly. Windows supports only the dynamic mode, and our task was to implement the memalloc layer for Windows without touching the upper layers, so that Windows port would benefit from every improvement in those layers, so that we have no violation. The challenge was that memalloc works in the following way. It allocates large portions of virtual memory area, and then it maps huge pages to predefined virtual addresses. It does so for multi-process support. Windows has no multi-process support yet, but we have to work this way in order to fit into the DPDK architecture. If you move to the next slide, you will see that Windows have several APIs that can deal with mapping memory at fixed virtual address, and also that can map huge pages, but only the newest APIs, the virtual alloc 2, that is available since Server 2019 or Windows 10, is really up to the task that we place for it in the DPDK, because not only do we need to reserve memory, but we also need to split the big reserved part of virtual memory into chunks, and then free one chunk and replace it with a mapped huge page. Unfortunately, there is an inherent race in this process between the freeing a chunk and mapping it, but for now, we have to live with it and hope that it doesn't fire eventually. After mapping a huge page, we need to get its physical address. On the next slide, there outline the tasks to do that. We need a kernel driver, and this driver must be secure. To be secure, it has to make sure that physical address it handles to the user space process is never used. Otherwise, we may introduce security vulnerability like data leakage. So we need to pin all the memory that we give physical addresses for, and we need to track allocated memory for each process, which is also subject to configurable limits. To do that, we use a special driver, word2fizz, on the next slide. How it works, when we allocate memory from the system, we get a memory region with virtual pages, and when application calls DPDK API and this driver in its turn, we recover the whole memory region, alloc it as a whole, check if it's physically contiguous, and give address back. And at the same time, we add this region to our tracking structures and enforce limits. word2fizz is the first of the two kernel drivers provided for Windows to make the DPDK work, and the next one is NetUIO. So, Pallavi, please.
Hello. My name is Pallavi Kadam, and I work at Intel as a software engineer. And today I'll be talking about Intel PMD support on Windows. So as mentioned earlier, as of DPDK version 21.05, we have I40E, that is 40 gig, and ICE 100 gig PMD support on Windows. And we did experience quite a few challenges earlier when enabling the code on DPDK code on Windows. So one of the challenge and requirement was to keep the code as much same as with the existing DPDK code. And the good part was that with the help of community and Microsoft folks, we were able to decide on the compiler used for Windows DPDK. Clang LLVM, and today we also have MinGW. So it was then possible to support GCC extensions such as typeoffs, attribute specifiers, and as well as to minimize if-def clutters in the common code. And to deal with OS-specific APIs, we had to replace and add additional header files as well. And yes, Intel PMDs are OS agnostic, and they can be easily portable on Windows. So we just took the existing PMD code and compiled it on a Windows platform. And we did experience few warnings such as typecasting, integer comparison, which were easy to resolve. And we also had to define new macros at one or two places as the Linux specific APIs were deprecated on Windows. So these are the next few immediate tasks planned. So as we have enabled I40E and ICE PMD on Windows, we have also verified that the basic RxTX and we will also make sure that other features such as RSS, receive side scaling, flow classification, etc., works on Windows, and uh, and also that it is full parity with the Linux performance. The next is the IVF. We are currently actually working on enabling IVF, that is Intel Adaptive Virtual Function PMD on Windows platform. On Windows DPDK, and hopefully this will be available soon to try out. This is mostly to execute the DPDK application in inside the VMs using SRIOV mode. And the next, we have also planned the automation using test cases to verify the performance and features for Intel PMDs. Next slide is the Windows DPDK setup from our lab. The right part, the table is showing the hardware details of our Windows server. And in the block diagram, the right block is the device under test, which has Windows Server 2019 OS installed. And the architecture of Windows DPDK is very similar to the Linux DPDK. As you can see in the user space, we are running L2 forward application using DPDK, DPDK stack and pole mode driver. And in kernel space, we have a NetUIO kernel module. And also, as Dmitry mentioned, we have a Word2Fizz as well now. And as you can see from the picture that the NetUIO is used for the initialization purpose and resource allocation, and thereafter L2 forward application will directly talk with the hardware using DPDK stack and pole mode driver, bypassing the kernel networking stack. And left block is Linux OS as a link partner, and we are using DPDK packet gen to send and receive the traffic. And next slide, we have a demo showcasing this L2 forward application app. It's I think it's playing. So you can see the left part is Linux packet generator, and right is DPDK L2 forward application running on Windows OS. And the application is starting and able to receive the packets on the left side on the Linux package. So yeah, this will be available to view later as well, and when the slides are available. And yeah, I would like to hand over to Tal now from NVIDIA to cover his part. Thank you, Tal. Over to you.
Hi, thank you, Pallavi. My name is Tal Shnaiderman. I'm from NVIDIA. Today I'll talk to you about the work we did to port the MLX5 PMD to work on Windows. So can you go back a slide before, Harini? Yeah, thanks. Okay, so MLX5 PMD, to those of you who familiar with it, is a bifurcated PMD, which means that, as you see in the diagram to your right, it's using the kernel driver of the NIC to create control path objects. The data path, of course, is directly through the hardware, but it needs the kernel driver for allow. So this challenge, this structure presented us with some challenges to port the PMD to Windows, mainly because APIs that the Linux kernel driver exposes the uses don't exist on the Windows kernel driver. For example, the verbs API. The API that does is exposed by the Windows kernel driver, which is called the Devix API, is used currently in the before the port was done, but it's used partially and needed on Windows as well. And the PMD is also used specific Linux libraries, Linux code, for example, pthreads and the OS system calls, which of course didn't exist on Windows, needed to be resolved. So next slide, please. Okay, so the effort that we did on our work to make MLX5 OS agnostic bifurcated PMD is, of course, reuse the maximum code in the control path. Everything that isn't OS specific will be used by both OSs and will not be changed. Any OS specific code will be isolated to functions which will be implemented by once for Windows and once for Linux. You can see it on the right. For example, there is an open device function. On Linux, it's implemented using verbs. On Windows, it's implemented using Devix. So the common code calls the same function. Depending on the OS that's running, a different implementation is called. Everything that was Linux specific regarding library calls and the OS calls were replaced by or enhanced by EAL, and for easy installation of the Devix package for DPDK developers to simply one-click install it and run a DPDK compilation, we added to the Win2, which is the Windows kernel driver, we added the Devix installation package available for the DPDK developers and users. So next slide, please. Okay, so here's the end result. On the left, you see the previous version. Depending on the OS, it's either using Devix only on Windows or all the APIs that used and continue to be used on Linux. Nothing has been changed. The enhancement was done on the Windows part, and the PMD is fully bifurcated on both OSs. So our status and the roadmap, as mentioned before, since DPDK 21.02, Windows MLX5 is supported using Win2 driver 2.60. It supports all of ConnectX 4 and higher NVIDIA cards. It supports both native setups and installing it on a Windows virtual machine using SRIOV. And of course, our future roadmap is to continue and enhancing the PMD in every DPDK and in every Windows Win2 release. You can see in DPDK 21.05, we enhanced more checksum offloads WinOF 2.70, which was released a week ago, enabled pair port RSS and promiscuous mode, and those are for the future release of WinOF 2.80. So now I'll show you a brief demo of our PMD running with the latest Windows kernel, which will use an L2 forward application, but also using an RSS an RSS cores with it. Yes. So you can see on the right there is. On the left, you see L2 forward running. It's running on 8 cores. Each core receiving packets, receiving and sending. The total number is 82, 83 million packets per second on 64-byte packets. You can also see that the way that Windows is using those 8 cores, and getting very high performance using a single MLX5 port. Okay, thanks. So next is Harini, I think.
Actually, it's me. So what I wanted to say that, as you have seen now, the DPDK supports large part of the DPDK, and we more and more often hit situations when we contribute Windows supporting patches to different parts of the DPDK, and we need people to review them, to test them, maybe. But most developers are really Linux people. Honestly, I'm one of them. My everyday system is Linux, so we need some tools that are free and that allow us to review the patches from familiar environment. What we have here for this task. First, from the early 2020, we have cross-compilation using MinGW, so that most of the development, if it's not a kernel driver, happens on Linux, if you like. Then to test Windows patches in QEMU, there are free development virtual machines from Microsoft, and there are also tools to develop drivers in them. And we also, as Windows maintainers, try hard to provide command line versions of all the actions you need to set up DPDK on Windows and to test the patches so that you can control it almost without mouse. What I wanted to say to all the developers of the DPDK, don't be afraid of this environment. It's unfamiliar, but it's new, and that's what is amazing about it.
Hey, thanks everyone. So quickly to wrap it up in the interest of time. So this is what I think we at Microsoft are looking at this time. So as summarized by both the Intel and the NVIDIA teams here, you can expect expanded hardware support and more featureful PMDs. And we'll have more hardware PMDs coming on board as well. We are also working on an interface to allow sharing of the NIC between the Windows kernel networking stack and the DPDK app, so that your app doesn't take over the entire NIC. So if you're interested in learning more about this, please drop me a note offline and I can get you some details. We're also going to be looking at adding unit tests and DTS tests, and supporting DPDK in a Windows VM eventually. Now we can do it with SRIOV depending on the PMD that you use, but we want it to be outside of the SRIOV scope as well. And then we also expect to add some compiler support in the future. So how can you help? So first up, I think I wanted to thank the team behind Windows Platform efforts so far, our tech board and governing board members that have kind of seamlessly helped us integrate, and our partners at NVIDIA, Intel, and our multiple ISVs and subject matter experts that have joined us from the community. If you want to learn more, please help us make this better. Provide us feedback. Go on to the Getting Started guide, and for any questions, drop a note to dpdkwin@microsoft.com. Thanks everybody. Thanks for the time.
Okay, so let's let's take it. So is this effort also on Windows 10 OS? Yes, it is Windows 10 and the Windows Server 2019. Then, do you plan VirtIO net support? Yes, it is planned. There were draft patches for that. It's just not yet upstreamed. It will be upstreamed, I think, in the nearest future. Then I think the third question is for Harini.
Yeah, I think at this time, it's on x86, but I think ARM64 support. I mean, ARM platform support is not ruled out. It's just not at this time a focus for us. So I can reach out to you offline, Hanap, and we can sync on that.
And again, there is the last question. Is it for server only or client versions of Windows? It is for both server and client.
As long as the NIC can work with the OS, you should be able to use it both on Windows 10 and server SKUs. All right, for any other questions, please drop us a note at dpdkwin@microsoft.com or reach out to us at dev@dpdk.org email list, and we'll try to get back to you. What is it for end users if DPDK on Windows OS? Oh, I don't quite follow the question. This you should be able to download and install DPDK both on Windows 10 SKUs and Windows Server SKUs. That should be possible. Any other questions? RC, I think I'm gonna ping you offline. I think we are out of time almost. So I will take up the AI to follow up with you offline. Thanks everyone. Thanks for the time today, and thanks all my partners here for making the time. Bye.
Bye bye.